All right, can everyone hear me? I think we're gonna get started now. For those of you who haven't met me, my name's Kelvin. I'm the other instructor for the class. Percy's not here today. I'm gonna be teaching this week's lectures on search, and you'll see me again later at the end of the month of October, teaching constraint satisfaction problems as well. Quick intro about myself. I used to be a PhD student here. I'm currently at Google working as a research scientist, and I'm excited to teach the course with you guys. So let's get started. We're going to be looking at search today. Search is a very important, essential aspect of artificial intelligence. It's really about reasoning into the future and making plans based on your simulation of the future. So just so I can kind of calibrate the course for people, how many people have heard of depth-first search? Okay, all right. How many people have heard of Dijkstra's algorithm? Okay, how many people have heard of dynamic programming? Okay, all right. Then this class is actually going to be somewhat of a review for many of you. Hopefully the lecture will kind of help you build connections between these things. But for the few people who haven't heard of this at all, the material in this section is really important because we're going to be building on the notation and the foundations here for reinforcement learning, adversarial games, and other subjects. So it's important that we get through this. But for those of you who do know this subject, it's going to be a bit of a review. So let's just start with a quick quiz question. Suppose you're a farmer, and you've got a cabbage, a goat, and a wolf on one side of a river, and you've got a boat that only holds two, and you've got to get all these guys across. Why you want to get a wolf across, I'm not really sure. But you've got to get it all across, and you have to be in the boat. The boat can only fit two, and the question is, how many times do you need to cross the river in order to get everything across? So I'm going to go ahead and reset this and activate it, and I'll give you guys a quick second to think about that question. All right, a quick second is up. It looks like people guessed 4, 5, and 6. All right, kind of clustering towards the middle. People are probably just saying, oh, it can't be 7 because that's the biggest number. Let's look at the solution from XKCD, and they do it in just 4 steps. So the first step, they take the goat across. Yeah, everybody was probably thinking that. Oh, I forgot to introduce an important part of the problem, which is that you cannot leave the goat with the cabbage, because the goat will eat the cabbage, and you can't leave the goat with the wolf, because the wolf will eat the goat. Totally missed that, but that's not an important part of this lecture. So you take the goat across first, then you return alone, then you take the cabbage across, and then you just leave the wolf, because nobody needs the wolf anyway. The actual solution to the problem takes 7 steps, and we'll see how to do that in just a second. Okay, so to situate what this course is going to be about in the grand scheme of the overall course, we are now moving from reflex-based models, where the system is kind of just reacting to a single input and making a single output, to state-based models, where the agent actually has to go through a sequence of states to get to some goal. And search is the most basic instantiation of that. So we're going to get started with that. And you can probably imagine a lot of applications for search. If you type a direction into Google Maps or something like that, you'll want to be able to find a route to some location, and that's essentially computing a sequence of actions that will satisfy some sort of objective, like shortest path, most scenic route, or something like that. Robotic motion planning is also a search problem, where the robot has to actually make a sequence of actions, send a sequence of actions to its motors to rotate a joint, to pick up a cup, or do some other action. Puzzle solving is very much in the same flavor. You've got to think several steps ahead to get to some kind of goal. And even some problems in natural language understanding are also search problems. So if I want to translate a sentence into another sentence, what I'm really doing is I'm taking a sequence of actions to output new words in the new language. And the objective is to preserve, of course, the meaning of the sentence in the original language and to make sure it's grammatical. So all of these are search problems. To kind of formally contrast that with the reflex-based models you saw earlier, in reflex-based models, you take some input, you build your function f, and it just produces a single output. So x could be a sentence, +1 could mean that that sentence has a positive sentiment, -1 means it has a negative sentiment, and you're done. But in this lecture, we'll be looking at problems where x is some kind of goal, and we want you to build a system that produces a sequence of actions to achieve something. So we have an action sequence now. All right. So as usual, we're going to be using this paradigm of thinking about modeling, inference, and learning. So in the context of search, modeling is going to be defining the search problem, defining what actions you can take, what your states are, and what the objective looks like. Learning is going to be any part of the model that you haven't been able to fully specify, such as the costs of taking actions. Maybe you need to learn that from the environment. That's something we're going to look at. And inference is, once you have that model, how do you actually compute a solution from it? So how do you find an optimal path? Today, we're going to be just looking at the modeling and the inference. We're going to save learning for Wednesday. And there are going to be 3 parts to this lecture. So the first part is tree search. This is the most basic instantiation. You're going to see how a search problem can be defined as a tree. Dynamic programming is going to basically take a look at how we can achieve exponential cost savings in certain types of search problems. And uniform cost search is going to give us a technique when we're searching over graphs with cycles as opposed to trees. All right, so let's start off with tree search by going into a little bit more detail about this problem that we were just talking about. So just for those people who just came in, we have to get a farmer, a cabbage, a goat, and a wolf across a river. And at any given time, you can't leave the cabbage and the goat on one side alone, unsupervised, because the goat will eat the cabbage. And likewise, you can't leave the wolf and the goat together because the wolf will eat the goat. So what are our actions? Our actions are basically, you can take any one of these things across the river. You can take a farmer across. You can take a farmer and a cabbage, C for cabbage, farmer goat across, farmer wolf. And likewise, you can come back with those same items. Any questions about what the actions are? OK. Now what we want to do is build a search tree, which sort of, in colloquial terms, is like you can think of as a decision tree of what to do. So the root of this tree is the start state. Everybody is on the left side of the river. Those 2 blue horizontal lines are the river, and everybody's on the left. So the first thing you could do is imagine taking the cabbage across, and you end up in this new state here. And it's marked in red because you've failed the constraints. On this state, the wolf eats the goat, and so you can terminate there. You can just decide that that failed. You can backtrack back up to the top, try another action. So this time the farmer goes across with the goat. Everything's fine. Try another action. Everything's fine. Keep trying actions until you either hit a state that is invalid. In this case, the goat eats the cabbage again. Or you keep trying actions until you finally succeed and get everyone to the other side. So that's the search tree. And you can enumerate all possible actions to build the entire tree. So the important thing to note here is that each node is a state of the world, and each edge represents an action that you took. All right, that's the basic picture. Let's put that in formal terms. So the root node is s sub start, the starting state. We're going to use this notation throughout the lecture. Actions is a function that takes a state and returns all possible actions you can take in that state. So depending on the state, you might be able to take different actions. Cost is the cost of that action. So it takes a state and the action that you apply in that state, and it tells you how much it costs. So in our case, crossing the river always costs 1. That's why you see the 1s on the edge of this tree. And finally, successor function takes a state and an action, and it tells you where you end up after you take that action. So that's kind of like the world model. It tells you, when I do this action, where do I end up? And of course, we need this final function to tell us when we've reached the end state. This is just isEnd. It returns true or false. All right, so now that we've got the basics down, let's look at another problem. This is just another one of these puzzle type problems. So suppose you're on a street with blocks numbered from 1 to n, and you start out in the first block, and your goal is to get to the last block of the street. So you can either walk from block to block, so going from s to s plus 1, the block immediately after, and that takes 1 minute. But there's a magic tram that if you get on this tram, you can go to a block. If you're in block S, you can go to 2s in just 2 minutes. So the question is how to travel from 1 to n in as little time as possible. So just to kind of build some intuition, is it better to take the tram early or later? Can someone kind of give an answer? Yeah, go ahead. Later. Yeah, later. Why?
Because then you'll be at a farther step, so when it doubles, it's...
OK, yeah, the reason is because you're farther out, so when you take the tram, you get 2x whatever you've already taken. So that's the right intuition. Now let's have a look at how we can solve this problem. So let's see. Let's define this transportation problem first in a bit of code here. just give me a second. All right, so I'm going to give you guys a spec of the problem because we're going to be using this for all the demos later in this section. So, all right, so we've got some class, transportation problem. This is going to describe the problem for us. It's going to have a few methods. So first of all, we want to actually initialize the problem and say what it is. And there's really only one thing that describes the problem, which is how many blocks there are. So we're going to go ahead and save that as n. Next thing we want to know is where do we start? That's pretty obvious. Can someone say what we want to return here? Just shout it. OK, it's 1. We're going to start at the beginning, which is the first block. OK, and then another easy one, which is the end state. So this checks when we're in the final state. And that's fairly straightforward. So we just want to check if the state equals the final state. Make sense? OK, cool. So this next function is actually clobbering together two of the functions that we showed in the slides. So this function is going to return both the successors of a state and the costs for the actions to get to those successors. So let me just write out a kind of little doc string for that first. So we're going to want to return a list of possible actions. And with each action, we're going to also show which new state you go to and the cost. And that's just going to be a triple. Does that make sense what this function returns? OK, cool. And yeah, apologies for the camel case and everything in the Python. I'm just kind of staying consistent with all the lecture notes. OK, cool. So we're going to build up this result list. And for every state, right, there are two things you can do. You can either walk or you can take the tram. So let's say you walk first. We're going to basically append to our result list. The first action we can take is walk. The state we're going to go to is just the next state, right? And the cost is going to be 1. Now, the other thing we can do is take the tram. And that's going to take us to 2 times our current state. And that's going to cost 2. Now, there are a few edge conditions we want to consider. We don't want to walk off the edge of the world. So if the state is, only if the state doesn't go past the end do we want to provide this as an option. And of course, only if this new state also doesn't go off the end of the world do we want to suggest that as an option, right? And then we return the result. So that's our definition of the transportation problem. Any questions about that? All right, cool. We're going to come back to this code in a bit. But now let's actually look at the technique for solving this problem. So since a lot of you are familiar with backtrack, sort of DFS, BFS, I'll go over this quickly. We're going to use backtracking search. So it's a procedure for exploring the entire search tree. Let's just do this on the whiteboard really quick. OK, so let's say you have some tree that looks like this. I'll visually depict backtracking search. So it's going to start out here, right here. Then it's going to take one of the actions and keep going until it hits a leaf node of the tree. Once it's hit a leaf node, it's going to backtrack upwards until it finds a node that has a free action that hasn't been taken yet. So in that case, it goes to here. Then it comes down here, finds a leaf node, backtracks here, no free actions, so backtracks up again. Free action here, ends here. That's the order of backtracking search. Another way of thinking about this, which is the way we're going to write this in code, is not in this sort of backtracking mindset, but more of a recursive mindset. So in the recursive mindset, you start out here, and you call a helper function that says, go explore everything down here. And it says, OK, I'll go explore it. And then it returns, and it says, I'm done. Then this guy says, all right, well, now just call exploration on this side too, and then we're done. So we're going to actually implement that recursive version. Now, quick question about the complexity of this. So can people tell me the space and time complexity of backtracking search? Assume that you have a tree that is big D actions deep, and the branching factor, in other words, the maximum number of children at each node is B. Can someone tell me the time complexity?
A lot.
A lot. OK, that's a good answer. All right, so memory first. Let's go with memory. So it's going to be O of big D. Why is that? So when we do backtracking search, remember that we have to be able to go back up. So these pointers only point downwards, which means we don't have a pointer back up to the previous things. And so we're going to have to remember our entire path as we were coming down. And that path is of length d, so the depth is d. And that's why the memory for backtracking search is O of big D. The time complexity is going to be O of b, little b to the big D. So what does that mean? Let's instantiate this with b equals 2, and let's say d equals 3. All right? So I can actually draw this tree because it's not too deep. OK, I guess that's more trouble than I thought. OK, so why does this end up being roughly O of b to the big D? Well, we have one node here. Then we have two nodes here, 4, 8. And so you can see that you're multiplying by the branching factor at every stage. So the last layer is going to have b to the big D number of nodes, right? So we know that at least, because the backtracking search explores all the nodes, we know that the cost in time is at least the number of nodes. And we know that there are at least b to the big D nodes. So it's at least O of b to the big D. But the question is, you might be thinking, well, what about all this other cruft on top that I explored? Why doesn't that factor into the runtime? The short answer is that this layer is so big that it dominates everything up here. And a kind of geometric intuition for that is the following. So suppose that the final layer is represented by this big block here. Then the layer right above it is half that, right? And the layer right above that is half of that. And the layer right above that one is half of that, and so on and so forth. And so you see that if you add together all the mass above the last layer, it's only going to be as big as the last layer. And I've only shown that for b equals 2, but it basically works out for all the other b's too. So that's how you know the time complexity of backtracking search. OK, cool. So I'm not going to go over this pseudocode because we're going to do a live demonstration of how to write that up. Any questions about the basic idea right now? OK, cool. So let's do backtracking search now. Backtracking search. And what this function is going to take is it's going to take a problem spec. So a problem is one of these guys right here, like transportation problem. Let's start by defining a few variables. So during the search, we're going to want to keep track of the best total cost, so the total cost of a path. And let's say to begin with that the cost is going to be infinity. So we're going to actually go through and find good paths. Recall that in this problem, we're trying to find the shortest path to some state that gets marked as an end state. And then we're also going to want to keep track of the history. So the history is the actual sequence of actions we took to get down to a particular state. And that can just be none for now. OK, so here's where the recursive function comes in. It's going to basically operate on a particular state that we're at. It's going to take the history of everything that came before it. And it will take the total cost of everything required to reach up until that state. So let's start with a base case. If this current state is actually a terminal state, one that finishes the game or whatever task we're working on. So if problem tells us that this state is the last state, people can see that, OK. What we want to do is say, all right, well, if the total cost up until this point is better than the best total cost that we've seen so far, then make sure to update the best total cost to be equal to the new total cost, and update the history to be equal to the new history. So I've committed a little Python bug here for people who are paying attention, but I'll fix that later. Just want to get through this to show kind of the overall approach. So, all right, if we've reached the end, then we just stop here, right? But let's suppose that we haven't actually reached the end. So this state is actually some sort of intermediate node in the tree, say like a node like this right here. All right, so what we want to do in that case is we've got this function that tells us all the successors and costs of a state. And recall that this is a list of different actions you can take. So we're going to loop over this list. So for action, new state, cost in here. We're looping over all the actions we can take. Simply call the same function again on the new state. And we have to make a modification here. So our history is now, it has one extra element on it, which is the action that we're taking, the new state that we're going to, and the cost. And we have to pass in a new total cost, which is the cost so far plus the cost of taking that action. Does that make sense? I want to pause here to see if there are any questions. Yeah.
What's the bug you mentioned?
Oh, okay, yeah. So the bug is that when you do assignment inside a function here, it creates a new variable in that scope, a new best total cost that shadows the previous one up here. So it doesn't overwrite this value, it just creates a new value. And I'm gonna fix that in a second. But yeah, any other questions? Way in the back.
Could you possibly increase the font size one more time?
Oh yeah, sure, for the benefit of people in the back. Is that better, font size wise? Let me no, that is not what I wanted. Okay, how's that? Okay, other questions, requests? Okay, cool. Great, so now let me just go ahead and fix the bug that I mentioned. What we're going to do is we're going to actually wrap each of these values in a list, and then anywhere we make an assignment to best total cost, we're going to modify that singleton element in the list. The details of Python are really not what I'm trying to illustrate here, so just don't worry about it. Okay, now the last thing we have to do, we've defined this recursive function, but we have to actually call it on the tree. And where do we want to call it? We want to call it at the root of the tree to make sure we cover the entire tree. So let's go ahead and call that. We're going to ask the problem for a start state. We're going to initialize our history as empty because we haven't done anything so far. And the total cost is going to start out as 0. All right, now once we've called this recursive function, it's going to go through and visit the entire tree. And it will have updated and modified these variables. So now if we just want to return the solution, we can just return this total cost here and this best history that we've got off here. All right, so that's the whole thing. And hopefully that code works. I'm really not sure. But let's give it a try. So we're going to start out with a problem that, let's say, maybe 10 blocks. And let's plug this into here and see what we get back. So I'm going to add a little print solution function to help us visualize the solution that we get, which will just unpack the history and the cost from the solution. And then let's say print the total cost and loop through the history and just print out everything in the history. All right, so hopefully that'll be good. Let's go ahead and print that out. And let's clear this. Tram demo. All right, so fortunately that works. Let me zoom this in here. And run that quickly again. So we see that if you have 6 blocks, the best thing to do is to walk for the first little bit, then once you hit 5, just double and go all the way to the end. Okay, so that's backtracking search. Now, let's do a quick modification of backtracking search, which we'll call depth first search. And so backtracking search really works on any search tree because it's just brute force. It just goes through the whole tree looking for solutions. Now, what happens if the cost of taking an action is 0? If the cost is 0, then it no longer matters that we find the shortest path, well, because they're all the same length, at least cost-wise, right? So as soon as you find any solution, you can just stop. And that's basically just what depth first search is. It's just backtracking search where you stop as soon as you find a solution. Quick question, does this change the space or time complexity of backtracking search? Does anybody want to venture a yes or no? Who thinks yes? And who thinks, okay, who thinks no? Okay, yeah, you're right that it doesn't change the complexity. And the basic reason why is if there's only one solution and it's the very last node in the tree that you visit, then all the time and space costs are the same. So everything is still the same. All right, now we're going to go to something that actually does have a different complexity. Some of this is probably review. So breadth first search is good in the case where the cost for every action is the same. So no matter what state or action you put into this cost function, it always gives the same value back. And the basic idea is to explore all nodes in order of increasing depth. So in this tree here, backtracking search would go all the way down, then come back up a little more. Breadth first search is going to say, explore everything at this level, then everything at this level, then everything at that level, and so on. Okay, so the reason this is good is because if all the costs are equal, as soon as you find something at a particular depth, let's say you find a solution at this depth, there's no reason to go to this level anymore, right? Because everything at this level is more expensive than everything at this level. And that's the basic idea of breadth first search. So the space is now much worse. And what is the reason why it's worse? So if some of you remember implementing breadth first search, you might remember that you have to maintain a queue of everything that you last visited. And from that queue, you then extend out from each node to the next level. So in order to go to the next level, you have to remember everything at one level. So the cost of that, the space required to store that level is going to be, in the worst case, O of b to the small d, where here d is the number of actions to the cheapest solution in the tree. So notation-wise, big D was the entire depth of the tree, and little d is the depth required to reach the minimum solution. All right, and then time is O of b to the little d. Does someone want to venture why that is? Okay, well, so basic idea is that once you hit a solution, you've explored everything above that point. So that's a tree with b to the little d order complexity number of nodes. Cool. So we've got this bad space complexity for breadth first search. Oh, there's a question in the back. All right.
Is this for finding the optimum solution or for finding some solution?
Okay, the question is this for finding an optimal solution or some solution? So our assumption here is that the cost of every action is the same. So this actually finds you an optimal solution. Maybe not the unique optimal solution, but one that has minimum cost. And the reason why is you're kind of going down this tree in depth. You're exploring an order of increasing depth. And the first time you find something, that thing also happens to have the cheapest cost among all the solutions you might find. Because if you go any deeper, those all cost more. So it finds an optimal solution. Okay. Now, let's see if we can avoid the massive b to the d exponential space cost. I'll get to a question in just a second. So, all right, the way we can do this is we can actually adapt depth first search with a slight trick so that we can get the same benefits as breadth first search. And the basic idea is we're going to run depth first search multiple times. So the first thing we'll do is we'll pretend that the tree only has one node. So cut everything below here and run depth first search, which means you'll just visit this node. The next thing we do is we pretend that the tree ends at depth 2 and run depth first search on that, and so on and so forth. So you see that we're still exploring in increasing depth, but now we're using depth first search at every stage. And what we learned about depth first search on an earlier slide is that the memory complexity of depth first search is only linear in the depth. So you only have to keep track of your ancestors, which means you get rid of the exponential space costs of breadth first search. So the space is now O of little d, and the time is still the same because you're still exploring that many number of nodes. So another point I wanted to make about this. Oh yeah, why is there a picture of a dog in the upper right corner? So the metaphor is that you kind of keep the dog on a tight leash first, and the dog kind of explores the immediate neighborhood. Then you loosen the leash, then let it explore more, and then kind of loosen it again. So that's sort of the mnemonic for remembering this. Okay, question in the back. Yeah,
I was just wondering for BFS, if you're looking at the worst case time complexity, why don't you consider the optimal solutions in the final depth? Like, wouldn't the worst case be a year to explore the whole tree?
Oh, okay. Yeah, so the question is, for BFS, why isn't the worst case the total depth of the tree? And so it's sort of more a trick of the notation that this isn't true. So here we've defined little d to be the length of the best path. And so if the length of the best path is the whole depth of the tree, then little d is equal to big D. And so yeah, in the worst case, it could be the full depth of the tree. Other questions? Okay, cool. So that's breadth first search and DFS with iterative deepening, which we call DFS ID. So that pretty much wraps up the tree search algorithms. Let's just have a quick overview because that was a lot of different things. So, all right, the first one we saw was DFS. It has good space complexity. This wasn't the first one we saw, but anyway, it has good space complexity, bad time complexity. But then again, if you look at all of these, they all have bad time complexity. They're all exponential. BFS has bad space complexity and bad time complexity. In fact, it's strictly dominated by DFS ID. So anytime you can do BFS, if you want to save space, you can just do DFS ID. The last one we've got here is backtracking. And backtracking takes kind of the worst linear space and the worst kind of time complexity. But notice that it works for any sort of action costs. These other two here only work for constant action costs. And DFS only works for 0 action costs. There's a question over there.
Why is the time for DFS O of D to the big D? If you know the solutions at little d, can't you just stop at little d?
Okay, that's a good question. So the question is, if we know, since we magically know this little d, which is the depth of the optimal solution, why can't we just say that DFS has a time complexity of O of B to the little d? The reason why is that DFS doesn't actually find the optimal solution first. So it may explore many deeper solutions before it hits the optimal one. And this has to do with the fact that it's not exploring things in order of depth.
But does it have to keep going for the deeper ones? If it doesn't find a solution by its exploration of little d, then it can't just say, well, this branch doesn't work anymore, we'll go back and some other way.
So maybe there's a case, like let's say that there's one node and it's the final node in the tree. Well, let's say you've got a tree and then you've got some solution which is, there's only one solution in the whole tree, and that is near the top, but it's kind of, if we're always exploring left, you can imagine it goes through almost the entire tree before it reaches that solution still. I can talk to you about it afterwards if you want. Yeah, okay, cool. Short summary is that all the tree search algorithms are always exponential time, and you can avoid exponential space always with one of these. Cool, so now we're going to move on to dynamic programming, and this is going to be about kind of saving time, exponential amounts of time over tree search. So the main idea with dynamic programming is the following. Suppose you're at some state, and you want to get to the end state. So we're going to think about all the costs required to get from your current state to the end. And you're going to break it up into 2 parts. The first part is just the cost of the very next action. And the second part is the cost of all remaining actions, which we'll call future cost. There are those 2 parts. And I'm going to write this out. Actually, no, I'm just going to point at the terms very carefully. So what is future cost? Future cost you can think of as here, the cost of the next action plus all future cost from the state that you end up at after your first action. So first action, remaining actions, right? And now I'm going to take a minimum over all the actions available to me. So if I try all the different actions I can from this position, and I compute their entire cost, and I pick the best one, then future cost here tells me the cost going forward from my current state. This equation is really important for reinforcement learning, for this lecture, for next lecture. So I want to make sure that people understand this. Any questions? Okay. Oh, okay, back there.
Future cost part,
Yeah.
intuitively I would have expected s plus 1 or s prime in the function there. Am I missing something?
Yeah, so in our transportation problem that we're doing right now, the next state is it's either s plus 1 or 2 times s, right? Depending on if you walked or you took the tram. But this successor function, what it does is it tells you what state you go to next. So it's the notation there that I don't want people to get tripped up on. Okay, cool. All right, so let's see a problem where we can actually use dynamic programming. So suppose we want to go from city 1 to city n, and you're only allowed to move forward. And it costs Cij to go from city I to city j. That's just some cost. I'm just giving it a variable name. So here's the search tree for how to do this problem if there are only 4 cities, if you want to get from city 1 to city 4. And it's pretty basic, right? So at city 2, you can only go to 3 or 4, and at 3, you can only go to 4. So that's why the tree has that structure. But now let's look at if we have 7 cities. Now the tree looks like this. And the important thing to note here is that there's actually a lot of repeated tree structure. So focus on the red 5. Sorry for people who are colorblind. The 5s are here, here, here. All along this, you can see the node 5. And if you look underneath 5, the structure is the same under every single 5, right? So if I'm doing tree search over this, I'm repeatedly exploring the same subtree underneath 5 over and over again. And the point of dynamic programming is to only do it once and eliminate this redundant computation. And the key observation is that once you're at 5, everything that came before, whatever cities you visited before 5, they don't matter in computing the future cost of 5, where the future cost is how much costs to go before I reach my goal state. All right, so that's the definition of a state. You saw in our overview slide that this set of lectures was all going to be about state. And what state really is about ignoring the past. It's somehow identifying some variable that lets you ignore all of your previous decisions. And once we've done that, the new graph that we have of the city problem looks like this. So it's no longer a tree. It's actually a directed acyclic graph. But you can see now that 1 can go to 3, 4, 5, 2, 3, 4, 5, 6. 2 can go to 3, 4, 5, 6, and so on and so forth. So no longer has tree structure. But what's really nice is we've eliminated all of the redundancy in the tree. It's a much smaller tree. And if you think about all the tree search algorithms we were looking at earlier, they're all, their runtime depends on how many nodes there are. So if you cut down the number of nodes, you cut down the runtime. All right, so dynamic programming actually looks almost just like backtracking search, except there's one extra line which says, if I've already computed the answer for this state, just return the pre-computed answer. That's really all that's going on here. Let's see a demo of that. Okay. Comment that out. Oh, no, not that one. Dynamic programming. Okay, so we're going to start out with a cache, which is going to help us store all the pre-computed solutions. It's a dictionary. And as you saw in the recurrence formulas, the main function that we'll be computing over and over again is the future cost of a state. So all costs going forward from that state. Let's start with the base case. So if we're in a state that is actually the end state, so we've reached the goal, then this is really easy. There's no more future cost. So we're just done there. Now, if the state happens to be something that we've seen before, this is also good. We can just return whatever thing was inside the cache. Now, the cache actually returns a structured object with a few things in it, but let's just say for now that the first thing in there is actually the future cost. Okay, so we've gotten rid of all the easy cases. Now we're in a situation where it's not the end state and we haven't computed a solution before, so we need to actually do some work here. Okay, so what is really going on here? Well, we've got basically this problem function, which gives us all the possible future states that we can go to from the current one. So we're going to loop over those. And again, it's an action, it's a new state, and a cost. And we're going to want to keep track of the one with the minimum cost. So let's define best action, which for now we're going to say has, let's say it's got infinitely bad cost. And the action is going to be none, and the new state is going to be none. And the cost here really doesn't matter either. So right now we have just a terrible best action. And we're going to loop through these, and we're going to say, if the current cost plus the, plus the future cost for the new state. So this is the recurrence that we're looking at now. Let's call this new cost is here. So let's say that if the new cost is less than the best action's cost, then we're going to update the best action to be this new cost, the action, the new state, and the cost. All right. And then we're going to put that inside our cache. And finally, we're going to return this best action, the total cost. Oh, okay. Oh, thanks. Okay, cool. So I deviated from my notes a little bit here to try and make things a little bit clearer. And hopefully I haven't actually made things worse. Any questions about this code so far? All right, so the main thing that I want to draw your attention to is we're looking at the next action we can take. And we're imagining a path where we took that action. So that action may not be optimal, but we're going to take it. And then from there, we're imagining that we do have the optimal path from that new state. So that's the future cost if I took this action next. And then what I'm doing is I'm saying, among these, if I'm kind of looking for the minimum cost one among these, so if the new cost that I have is better than the best one so far, so this right here is storing the total cost right here, then I'll go ahead and replace the result with this one right here. And then I'm putting that in the cache, and then I'm returning it. All right. So let's see if that works now. I'm going to go ahead and replace this with dynamic programming and see if we get the same result. Oh, OK. All right. Time to default to my other solution. Let's have a look at the backup one that I had. All right, more or less the same idea. I'll follow up with, oh, I actually didn't implement the rest of the function, which was to actually call it. All right, well, let me walk through the rest of it. Yep, sorry, noob error. OK, so we've got this state. OK, I implemented future cost, but I have to actually call the function. So we go to the problem, and we create a start state. And then from there, we want to compute the future cost of the start state. So the future cost of the start state is actually the best cost for the entire problem. And then once we do that, I actually need to build up the history of what the solution was, because I wasn't actually keeping track of that. I only just basically computed the minimum cost, but I didn't store the history. But fortunately, the cache contains a fair number of, it already contains information in it about which action was best at every state. So first I'll start with an empty history. And then what I'll do is, so I start at my start state. And for each state, I'll look in the cache and the cache tells me what was the best action that we found for that state. So that's this action here, and what was the next state, and what was the cost of that individual action. So the history will first record that best action in that position, and then I'll update state to be this new state right here. So because the cache has the optimal move at every state, I can look through it to find the optimal path from there. And then I'm going to return the total cost and the history. So let's actually comment this out for now and have a quick look at that. Comment this out too. So let's say we have a number of blocks that's 100. Okay, so we get some solution which involves walking some amount, taking the tram some amount. Let's compare the speed of this to backtracking search. So suppose that we did backtracking search instead, and we had 1,000 as the number of blocks. So notice that I've already hit run on this, and it's still going. It takes quite a while to do that exponential search. I'll go ahead and terminate that. If we switch over and use dynamic programming, giving it the same problem size, the result is almost instantaneous. So there's huge savings to be had with dynamic programming. All right, let's move on from here. So the main idea with dynamic programming, that's very important actually. So we already gave the main idea, which is that you're memoizing redundant computation. But one assumption that you need is that the graph that you're operating on does not have any cycles in it. So why is a cycle bad? Let's look at a quick example. Suppose that you had a graph that looked like this. So your start state is here, and you're going along, and there's some end state here. But let's say there's a cycle that takes you like this. So in the code of dynamic programming, you're going to say, all right, what is the optimal solution from this node? Well, I found one solution which goes this way for very little cost, but I also need to explore this way. So I'll go here, and it'll say, OK, well, I need to explore this way, and then I need to explore this way. And then this function gets called again, and it says, I found a path here, but I need to look here. And so it'll just keep going, and it'll never finish. So that's why you can't have cycles in dynamic programming. Just to make sure, so we're going to look at a solution to this. Basically, uniform cost search is going to help us eliminate the problem with cycles. But to make sure we get the key idea of dynamic programming, the main idea is that you find some state that allows you to forget about all actions in the past. That's really what allows you to save on computation. And just so we can be sure that this approach is actually quite flexible, consider a modified version of this problem where you're not allowed to visit 3 odd cities in a row. Same problem, you have to get from the first city to the last, but you can't visit 3 odd cities in a row. So now, just looking at your current city, is that state sufficient to help you decide what to do next going forward? It's not. Here's an example why. So let's say you're at city 1, and then you go to city 3, and now you're considering whether to go to city 4 or 5. So if you go to 5, you've created 3 odd cities in a row. But if all you know is that you're at 3, you have no memory of where you were before. And so using 3 as the state is not going to work here, because it's going to allow you to do actions that are invalid. Turns out you can fix it by basically just looking at your current city and remembering your previous one. And you can do even better than that by simply remembering whether the previous city was odd or not. So now let's think about the size of our state space. Before, the number of states was just the number of cities. In this version, where we remember the previous one and the current one, the number of states is n squared, where n is the number of cities. And if we just remember whether the previous city was odd or not, then the number of states is 2n. So making sure to kind of minimize the size of the state is important. It changes the overall runtime of the algorithm. And here's a quick demonstration of that. I think I already did this on the whiteboard, so we can go ahead and skip over this. Let's do another quick quiz. So suppose you're traveling from city 1 to city n, and the requirement is that you visit at least 3 odd cities. In that case, what would be a good definition of the state? So let me activate this here and give people a chance to think about it. Okay, moment of truth. And my browser broke. Oh. Okay, here, oh shit. Sorry. Here we are. Okay, these are the answers. So I can't really, okay, some people say 3. Not really sure what that means. Okay, but the one down here, okay, some of them are definitely getting at the right idea, which is your current city and the number of odd cities you've visited so far. But that's actually, you can do better than the number of odd cities. Once you've visited 3 odd cities, you don't really need to think about how many more you visited. So really, you only need to store 0, 1, 2, or 3. Here's a graph of what that looks like, the state graph. This diagram I never thought was that clear, so we'll just skip over that one. Okay. Okay, one more. Actually, just for the sake of time, let's skip this quiz question. I think people get the idea that you need to shrink the size of the state space and remember as little information about the past as possible. So we've encountered this notion of state. Dynamic programming is basically backtracking search with memoization, which gives you potentially exponential savings over tree search. And now we're going to address the question of, okay, dynamic programming only works for acyclic graphs. So what if there are cycles in the graph? And that brings us to uniform cost search, which is the last third of the lecture. For people who have studied algo, uniform cost search is another name for Dijkstra's. There are some nuanced differences, but you will be seeing kind of Dijkstra's here. So I'm going to skip over this slide because I think that we've got a better way to describe it. All right, so the key idea of Dijkstra's, or uniform cost search, is that we're going to be visiting things in order of the cost it takes to reach them. So how does that look? Oh, and another assumption that we're going to need for this to work is that we're going to need all the costs to be positive. And I'll come back to why we need the costs to be positive in a bit. Let's just have a quick look at what uniform cost search visually looks like. Okay, so what you're seeing here is we started out in the bottom corner here, and it's basically emanating outwards. And here the cost is simply the kind of distance it takes to get there. And you see this green line that's moving around. You'll notice that at every stage, the green line is always sort of the same length, like the line is incrementally increasing, right? So it's visiting states in order of their cost to reach them. That's visually what's happening. Okay, and the, how do I close this thing? Okay, the other main idea is once you reach a goal state, there's no need to continue searching anymore. You can stop the algorithm. So why is that? The reason why is because you're searching for things in order of their cost. If you find anything later on in the algorithm, it's going to cost more than the one that you found earlier. So as soon as you find something, you can stop. And here's mechanistically how uniform cost search works. So we're going to have some set of states that are explored states. They're states that we've already found an optimal path to. We're going to have some frontier, which is states that we've seen. In other words, they're neighbors of explored states, but we still haven't figured out how to get there cheaply yet. And then we're going to have unexplored states, which we simply haven't seen at all. So there's 3 types of states. And what we're going to do is, for each frontier, figure out the shortest path, add them to the explored set, and keep building out the frontier. Let's do a whiteboard example. So, all right. We've got a very simple graph here. A, B, C, and D. And it costs 1 to get from A to B. It costs 100 to get from A to C. 100 here, 1 here, and 1 here. So you can probably see very easily that the best path is this way. And how does uniform cross search find it? So we start out with only A in the explored set. That's the only thing we've seen. The frontier then is everything we can access from the explored set, which is here and here. So, all right, these are the things in the frontier. We put them into a priority queue, which sorts things by the cost of reaching them. So if we pop something off the priority queue, are we going to pop B off or are we going to pop C off? B, okay, because B is a lot cheaper to reach. So we pop B off and we get here. And once we've gotten here, we know that this is the cheapest way to get there because our algorithm is exploring things in order of cost. So now this thing here becomes the explored set. And our frontier, C is still in the frontier, and D is in the frontier now too, because we can reach it from our explored set. All right, now, next question, are we going to pop C or D off? C, okay, so why? Not because there's a 100 cost path here, but because we found a path that costs 1 and 1 here. So that's only 2. 2 beats 100 and it beats this 100, so we go here. Okay, so now this whole thing is in the explored set, and then there's just D left, and there are 2 paths to reach it, and we pick the cheap one, and we're done. So with this picture, we can probably also see, okay, this picture is not going to help us, but now let me explain why we can't have negative costs. So suppose you had some path that looked like this, and you had something like negative 1,000 here, and you had something like 900 here. I don't know if I'm going to be able to give an example off the bat, but the basic idea is that with this approach, you think that you're going down a path that costs a lot, but really you're going to sort of relieve that debt later. And so it breaks the idea that the first thing you find is the best, because something you find later could actually catch up by taking a negative edge. And so that's why we can't have negative costs. All right, so here's the pseudocode for uniform cost search, but I think it's probably just better if we do another demonstration. Okay. So even though I've got it here, let me just build it out for you guys so that you can see how it works. Yeah.
So, in the previous example, when we found a better way to get to a node that was already in our priority queue,
yeah,
were we replacing that node in our priority queue with the new best way?
Oh, so I mean, there are multiple ways you can do it, but you can. So you could just put in 2 paths. So really, the priority queue, you can think of it either as you can either think of it as replacing that node's best path with the new one you found, or you can think of the priority queue as being full of paths, and you're just extending the shortest path.
Okay. So technically, then couldn't you modify the algorithm slightly to make it work for having negative ways?
What's your proposed modification? I feel like that would be a paper if you.
I should probably think about it.
Okay, sure. We can talk about it. Cool. Any other questions? Yes.
What if like you at the start you have 2 different paths you can take, one with a higher cost, one with a lower cost,
Yeah.
and then there's not much of a difference, and then the one with the lower cost ends up having more cost later on,
Yeah.
and you will never explore the other path that may end up like the sum might be.
Okay, yeah. So the question is like, what if early on it appears like one is cheaper and the other one is more expensive, but eventually the cheaper one gets more expensive and the expensive one gets cheaper? So what happens is that uniform cost search will first extend the cheap one until it gets expensive, and then it'll be like, oh, this is actually harder than I thought. Let me actually extend the other one. And so it will, because at some point, the one that you said kind of was deceptively cheap, it will become more expensive than the one that looked expensive up front. And at that point, the expensive one will then get extended first. And so when you have 2 paths that are almost the same cost, uniform cost search doesn't help you that much because it will essentially end up exploring almost all of them, of both sides. Yeah, other questions? Over there.
So for the graph you've drawn on the board, what if you just added 1,000 to all of the paths?
Oh yeah, okay. So the common thing that people think to do is to just find the most negative thing in your graph and then just add that to every edge so that now everything is positive, right? So the problem with that is that if you have one path, let's say that costs 1,000, and then you have another path that's made of 1,000 length 1 edges, and you add 1,000 to each of them, then the one that's made of smaller edges actually became way longer than the one that just had one edge. So you can't just like add a sort of bias term to everything. Yeah. Right, to clarify, the question was why can't you just move all the numbers up until they're positive? Okay, cool. All right, so we're gonna start with having our frontier function, which is a priority queue. For people who aren't familiar with priority queues, they're basically a data structure that allows you to find the minimum element inside it, and it takes log of n time to remove that element, where n is the number of things in the queue. So the first thing we're going to do is put the start state into the frontier. So that's the first place we're going to explore. Now what we're going to do is repeatedly do the following. We're going to take the frontier, and we're going to remove the smallest element, so the cheapest thing from here. And the frontier is basically removing things based on cost. Now let's do our base case. So if we've hit the final state, then good job. That's the final cost. In this implementation, I'm going to skip tracking the history because that's just an extra thing to keep track of. And all right, if we haven't reached an end state, then again, I'm going to want to loop over all the actions that I can take from this state right here. And I'm going to put those into the frontier. So the cost of this new state is the cost that it took for me to get to this state plus the cost of crossing that one edge to get to the new one. Now, quick question, is this the best cost that is possible to reach this new state? No, yeah, it is not. It's just one of the ways to reach it. The priority queue is actually going to return us the shortest one. We're just giving it as an option into the priority queue. All right. And then once we've done that, we're done. So the function is always going to return from here when we eventually hit some sort of end state. Okay, now let's plug this in and just see if it works. We actually want, yes, this version. Okay, so it gives us some cost. I guess that's not particularly interesting, but that's the overall implementation. Does anyone have any questions about this implementation right here? Okay, cool. All right, so that's uniform cost search. And this theorem here is talking about the correctness of search. I think the main intuition I've already given you, which is just that because things are being explored in order, as soon as you find a solution, you found the optimal solution to the problem. All right, cool. So we can have a look now between dynamic programming and uniform cost search, and we can ask ourselves what their relative advantages and disadvantages are. So dynamic programming, as we said, cannot handle cycles, but uniform cost search can. The other thing about DP is that it can handle any action costs, whereas uniform cost search has to take positive costs. And finally, the time-space trade-off is a little bit more nuanced. So in this chart here, let's suppose this big rectangle I'm about to draw is the total size of the state space. So this is big N. And let's say that this point right here is the start state. Start. And this is the end. Let's draw it here. Let's say this is the end state. So uniform cost search you can think of as exploring everything in this ball, everything that is within this distance from the start state. This is going to be called little n. So dynamic programming computes a future cost for every state in the entire state space. So that's why it's O of big N. Whereas uniform cost search only looks at these little n states. But why is the log n there? So the log n is there because we need to pop every state off a priority queue, and the priority queue requires log n time to pop something off. So we're doing it n times, and each time it's log n. So that's how we get n log n. Cool. It looks like I might have gone a little bit too quickly. I think we're almost reaching the end of the lecture now. So to give a quick recap, we looked at tree search today. Tree search is very memory efficient. It's only linear in the depth of the solution. So you can explore very large spaces, but the runtime is exponential in the worst case. We've looked at this notion of state, which is all about summarizing all of our past actions so that we have all the information we need to make future actions optimally. And that's where dynamic programming got introduced. And finally, we looked at graph search, which allows us to basically shrink the overall size of the tree and also achieve exponential savings. So next time, we're going to be looking at how to learn the actual costs on the edges. So if you have an expert demonstrating what they believe to be an optimal path, and they haven't told you what costs are on the edges, how can you learn what the cost of that path is just by looking at expert demonstrations? And we'll also be looking at searching faster with A star. So A star is going to allow us to bring kind of prior world knowledge into the problem to say, oh, even if I don't explore the whole tree, this direction is probably better than other directions. So we'll be looking at that next. And because I guess we have plenty of extra time, I'll stick around for questions. But other than that, we're all done.
Back there.